Hi, I'm Zeev. I'm in the last year of my PhD at CMU, and today I'm excited to tell you about some work I've been doing with Isaac Grosof and Michael Mitzenmacher about scheduling with noisy information. So, to set the scene, our work fits into the area of algorithms with predictions. Specifically, we're thinking about scheduling with predictions. So, we're thinking about jobs in a queue and deciding what order to serve the jobs in to minimize their average delay. And the type of predictions we're going to be working with are job size predictions. That is, predictions about how long each job will take to serve. And the twist is that we're going to be doing all of this from a stochastic perspective. And we're choosing the stochastic perspective because there's lots of systems in practice that are well modeled by stochastic assumptions. And so we think that this sort of stochastic modeling theory approach is going to provide the right insights for scheduling in those sorts of systems. So the question we're going to answer today is, how do we schedule to minimize delay with noisy size estimates? And so let me start by talking a bit more about what scheduling and delay even are. Then I'll talk about the specific noise models we assume. And finally, I'll discuss what can we hope to achieve in terms of minimizing delay, right? What are the right goalposts to aim for? Okay, so let me start by introducing just what are scheduling and delay. So we're scheduling in a single server queuing system in this work. So here's a server. It does some sort of useful work, provides some sort of useful service. Here's a queue. This holds jobs that are waiting for service. We're going to assume unlimited capacity. And then this is a job that needs some sort of work done at the server. So the amount of work the job needs done is called its size. We'll measure size in units of time, the amount of time it needs service for. And we'll represent that service as the job is a test tube and it's getting filled with water. So we can talk about the remaining size of a job. That's the amount of work left. And we can also talk about the age of the job. That's the amount of work that's been done so far. These are also measured in units of time. So we have arrivals to the system, jobs arriving in online fashion. So here's one job that's small, here's a bigger job, and the arrivals happen according to some stochastic process. So there's some arrival rate lambda, and jobs arrive at this average rate at completely random times, formally a Poisson process. There's some job size distribution from which each job size is independently drawn. And this gives the system a certain load, which is the average arrival rate times the average job size. And you can think of load as the fraction of time the server has to be busy in order to keep up with all these arrivals, in order to get all the jobs done. And in order for the system to be stable, load has to be less than 1. So that's what we're going to assume. Beyond assuming that load is less than 1, we won't make any further assumptions that limit, say, the job size distribution. This is important because in practice, different types of applications have very different looking job size distributions. Okay, so that's the sort of stochastic queuing model we're working with. So let's continue the story of maybe this job at the server, eventually its age reaches its size. This job is now complete, and so it exits the system. The total amount of time the job spent in the system between its arrival and departure is called the job's response time. And so this is what I mean when I say delay. For the rest of this talk, delay is a synonym for response time of jobs. Okay, so this job has exited the system, and we now have to decide what job gets to go into service next. This is the domain of the scheduling policy, which decides at every moment in time which job to serve. And it's a preemptive process, so we can decide to switch out one job for another, and we don't lose any progress or incur any overhead to do this preemption. Okay, so we've gone over single server scheduling and what delay means. So what do we mean when we're saying we're trying to optimize delay? So remember that delay means response time. But we're not just going to look at one job's response time because we have this whole stream of arriving jobs. We're going to have a response time distribution where if I look at a really long arrival sequence and I ask, how long was just this job in the system, that job, and so on and so forth, I get some distribution, which I'll denote by capital T. And this distribution is affected by the arrival process and the scheduling policy. And so my goal in this work is going to be to design a scheduling policy that minimizes mean response time, the average delay over all jobs in this long arrival sequence. And so as a warm-up, let's consider a sort of easy version of the problem. Let's suppose the job sizes are known. So when a job walks into the system, it says, here is my size, and it's exactly right. How would we schedule to minimize mean response time then? So it turns out that the key idea is that it's better to serve a small job in front of a big job than vice versa. So the policy that takes this to its natural conclusion is called SRPT, stands for shortest remaining processing time. And that name basically describes what the scheduling policy does. It always serves the job of least remaining size. And so it's not too hard to show that SRPT is optimal in terms of minimizing mean response time when you have access to exact job size information. But in this talk, we don't have access to exact job size information. We only have access to noisy size estimates. So when a job walks into our system, if we're the scheduler, we see an estimated size Z, and we know the true size is somewhere around Z, but we don't know exactly where. So what precise assumptions are we going to make about the noise model? We're going to assume something that we call beta alpha bounded noise. So this is saying that if a job has true size S, then its estimated size will be within a factor of beta below or alpha above the true size S. So the mnemonic is beta is for below, alpha is for above. Another perspective on this is that if we look at a job in our system and it has estimated size Z, that means its true size is somewhere between Z over alpha and Z over beta. Okay, so this is the assumption we're going to make on the noise. And we're also going to make an assumption about how these true and estimated sizes are generated, right? So we said already that true sizes are generated by drawing from a distribution. We're actually going to assume that pairs of true and estimated sizes are drawn from some joint distribution. But we're not going to make any particular assumption about what this joint distribution is beyond the fact that it's beta alpha bounded. And so we're going to try and design a scheduling policy that works for any joint distribution and for any value of alpha or beta. So we're basically going to try and design a noise oblivious policy that works well no matter how much noise there is. And you can also think of this as a kind of semi-adversarial version of the problem, in that we could let an adversary choose the particular joint distribution, and we want our policy to perform well no matter what the adversary chooses. Okay, so this is the noise model we're working with. And I want to mention that a variation of this model has been studied before in a worst case setting. Specifically, this beta alpha bounded noise assumption has been studied in a line of work recently by Azar, Leonardi, and Tuitu at Stock and Soda publications recently. So I think it's exciting that we're developing sort of concurrent lines of work in both the worst case and stochastic settings. Okay, so this is the noise model we're going to be working with. Beta alpha bounded noises that come from some joint distribution, but we're not going to make any assumptions about what that distribution is, and we're going to try and schedule without actually knowing the distribution. So in this setting, what's a reasonable goal in terms of mean response time? And so if we look at the algorithms with predictions literature, there are a few kind of common goals that we see when people design algorithms for predictions. So for example, consistency is one common goal, which is about having good performance when the predictions are very good. So formally, we're going to call a policy C consistent for some constant C if that policy P's approximation ratio, namely its mean response time ratio relative to SRPT, converges to C or less as alpha and beta converge to 1. So that's consistency. It's all about good performance under low noise. What if there's tons of noise? What if the predictions are almost useless? So a goal that we'd aim for in that setting is robustness. So formally, we'll define our robustness as saying P is R robust if its approximation ratio is always at most R for all alpha and beta. Unfortunately, it turns out our robustness, at least for constant R, isn't achievable in our setting. And so we can't hope for robustness. Okay, so far we've talked about the case of low noise and of like really high noise. What if we have medium noise? What's a goal we might aim for there, especially given that we can't get robustness? So this is something that people often try to do in the algorithms with predictions literature, but it doesn't have as sort of common a name. So we call this concept graceful degradation, or in this talk, just graceful for short. So we call a policy G graceful if its approximation ratio is bounded by G times some measure of the prediction quality. And in our setting, the natural measure of quality turns out to be this ratio alpha over beta. It's kind of the multiplicative size window in which the size estimate lives. Okay, and so I would call this concept of G gracefulness, it's not a new thing. It's a slightly newish that we're sort of calling it out, because I think it definitely doesn't have the same sort of recognition that consistency and robustness have. Some work that studies what we would call gracefulness will end up calling it robustness. So I think it's important to kind of distinguish between gracefulness as being a different thing from robustness. And so that's something we're trying to do in our work. Okay, so we can hope to achieve consistency and gracefulness. And that's exactly what we're able to do. So our main contribution is introducing a scheduling policy that's the first that has been proven to be both consistent and graceful in this stochastic scheduling setting. So in terms of gracefulness, we have constant G equals 3.5, and for consistency, C equals 1. So it's perfect consistency. And so what's new here is both the policy itself and these proofs that it's graceful and consistent. And one thing I want to point out about consistency in particular is that this consistency result with C equals 1 is impossible to achieve in the worst case. And so this is one difference between the stochastic setting and the worst case setting. All right, so let's recap this contribution. We introduced the first scheduling policy that is both consistent and graceful. And so in the rest of this talk, I'm going to dissect this contribution. So we'll ask questions like, what is this new policy? And how do we bound its performance? But before we get there, I want to say a few words about what policy even means. And so there's a vast design space of possible scheduling policies. And one thing we did to help ourselves out was to narrow our focus to a subclass of scheduling policies. Still a very broad class of scheduling policies, but something that was a bit easier to think about. And for which some queuing theory existed to kind of help us evaluate scheduling policies. And I'll get to a bit of that later. So the design space we ended up looking at was something called scheduling policies that can be described as rank functions. So remember that a job's age is the amount of time it's been in service so far. It turns out that lots of policies in the scheduling literature can be described as a job having some priority, which we'll call a rank, that varies as a function of age. So we're going to say that rank is some numerical priority. Lower number means better priority. The server's always going to serve whichever job has the lowest rank. And this rank can vary as a function of a job's age and also perhaps of its static characteristics. In our case, that's going to mean size and estimated size. As an example, SRPT fits into this framework. It has the rank function S minus A. That is, a job's rank is its remaining size. And so SRPT always serves the job of least remaining size. Now, of course, we're going to try and design a rank function that doesn't use S, right? Because we don't have access to the true sizes. So if we don't have S, but we do have Z, what might we do instead of SRPT? Well, the obvious idea is, well, Z is going to be close enough to S, so let's just use Z instead. So this is a policy that we call naive. It's the naive translation of SRPT into the size estimate setting. Okay, and naive, of course, also has a rank function. It's just Z minus A. And so in this work, we're going to be focusing on the design space of policies that can be described as rank functions. And so when we're trying to design a policy, we're really asking the question, what's the right rank function? So let's start by looking at naive again. Is naive the right rank function? Is it going to be consistent and robust? And we might hope that naive performs well because Z is close enough to S that Z minus A is close enough to S minus A, and the scheduling policies should do basically the same thing. But unfortunately, it turns out naive is not even consistent. And the big problem with naive is that its rank can go negative. So what happens when a job has negative rank? Well, every job arriving into the system has positive rank. And this job that just went negative has the lowest rank in the system because it's the one in service. And so no other job is going to catch it it's going to be non-preemptible for the rest of its time in the system. And because we have multiplicative estimation error, a really big job that gets underestimated by even a small factor could spend a really long time with negative rank being non-preemptible. And that can be really bad news for our mean response time. And so naive is not even consistent. All right, so what can we do instead? How can we fix this problem of naive? Well, I said the rank function going negative was a problem. What if we just didn't do that, right? So this leads to a policy called checkmark. And checkmark is consistent. But unfortunately, checkmark is not graceful, at least not when beta is less than 1/2. So what goes wrong when beta is less than 1/2? Well, first let's remember what beta less than 1/2 means. That means that a job's estimated size can be less than 1/2 of its true size. So in the picture, that would look like a job's true size being all the way out here. And so let's think about what will happen for this job with this true size S and this much smaller estimated size Z over the course of its service under checkmark. So by the time a job's reaching the end of its time in service, its rank will have exceeded its initial rank. And this is bad news because whenever you reach a new worst rank of your time so far in the system, that's an invitation for other jobs that have been waiting with rank that was higher than you. You might have just reached their rank, and so those jobs can now preempt you. And so whenever you reach a new worst rank, preemption becomes likely. And so checkmark has this tendency of preempting jobs just as they're about to finish. And so checkmark is not graceful. Okay, I'm out of room in my gray box of policies that won't work, so we have to come up with the right one this time. How are we going to fix the problem with checkmark? Well, I told you that the problem with checkmark was all about exceeding this initial rank. So what if we just didn't do that? So this leads to a policy called radical. Radical doesn't go negative and doesn't exceed the initial rank of a job. And we call the policy radical both because it vaguely looks like a square root sign and because it has radically good performance properties. It is the one consistent 3.5 graceful policy we've been looking for. And so in the rest of this talk, I'm going to explain how we compare radical's performance to SRPT's performance, which is at the core of how we prove our consistency and gracefulness results. Unfortunately, it turns out to be pretty hard to directly compare radical to SRPT. It's because even though their rank functions kind of happen to coincide when there's low noise, when there's no noise. If there's even a little bit of noise, then the fact that radical starts at Z and then goes down to Z turns out to be different enough from starting at S and going down to S that it's hard to do this direct comparison. And so what we did is we did this comparison by way of a third policy called scale, which is sort of partway between radical's rank function and SRPT's rank function. So like radical, a job's initial rank is Z. But like SRPT, a job's rank scales linearly down and ends at 0 by the time age equals size S. And so what this means is that we can't actually implement scale without knowing a job's true size. So you wouldn't really use the scale policy in practice, but it's helpful for analysis because we can compare radical to scale and then compare scale to SRPT. Okay, so how are we going to do these comparisons? So this is where the second sentence of this talk comes in, which was that I'm in the last year of my PhD. So the thesis I'm writing is all about how do we analyze scheduling policies in stochastic queuing systems. And my thesis is all about two new tools that I've developed along with my collaborators, including Isaac Grosof. And these new tools help us analyze policies like radical, scale, and SRPT. And in fact, I'm really excited about this paper in particular because for the first time, we had to use both tools. So I'm going to tell you a little bit about each of them. So the first tool is SOAP, which we use to compare radical to scale. And the second tool is called WINE, which we use to compare scale to SRPT. So I'm going to say just a few words about SOAP, and then I'll go a bit more depth into WINE. And the reason I'm going to focus a bit more on WINE today is because WINE is actually potentially useful even for worst case scheduling questions. And so I think that's a really important one to share with the ITCS community. Okay, so let's start with how we compare radical to scale using this tool SOAP. So SOAP stands for Schedule Ordered by Age-Based Priority. And what SOAP does is it takes basically any stochastic arrival process and any rank function and yields the response time distribution. It's a sort of complicated formula. The formula for mean response time is a little bit simpler, but still pretty complicated. And so I'm going to defer the details to the paper. But the basic version is that because the radical and scale rank functions are close enough to each other, and in particular because they both have initial rank z and never exceed that initial rank z, the policies are close enough that SOAP yields similar enough mean response times for them. So that's how we do that first comparison. Let's now talk about comparing scale to SRPT using WINE. So WINE stands for Work Integral Number Equality. And so unlike SOAP, which directly gave us response time, WINE is a way to get the number of jobs in the system. But this is fine because there's a famous result in queuing theory called Little's Law, which says that the mean response time is directly proportional to the mean number of jobs for any fixed arrival rate. And so the way WINE gets us the number of jobs in the system is via this other quantity called R work, which I'll define soon. And so what WINE does is it reduces the problem of analyzing mean response time to the problem of analyzing R work, or in our case, comparing scale's R work to SRPT's R work. So in the rest of my talk, I'm going to answer some questions about WINE. First, what is R work? Second, how does WINE give us n, the number of jobs, from R work? And then finally, how do we use this to bound scale's mean response time? So let's start by defining R work. And before I define R work, let me just define work without the R. So when queuing theorists talk about work, they just mean the total remaining size of all jobs in the system. R work is going to be a filtered out version of this total work. So let's let R be some threshold. R work is the total remaining size of all jobs, where I'm only counting the jobs that are R and smaller in terms of their remaining size. So I like to visualize R work as follows. I've got some threshold R glasses. Let me align the jobs by remaining size. And so when I put on these glasses, they're going to hide the jobs that have remaining size above the threshold R. If I look at all the jobs that I can see through the glasses and I add up their remaining sizes, that's R work. And so the importance of R work is that WINE tells us how to get the number of jobs from an R work integral, because remember, WINE stands for Work Integral Number Equality. And so WINE says that under any scheduling policy, we get number of jobs from this R work integral. And so what we did is we basically bounded scale's R work in terms of SRPT's R work. Here's what we showed. We showed specifically that scale's R work was less than or equal to SRPT's mean alpha over beta R work. The intuition here is that scale is always serving a job not necessarily of least remaining size, but within an alpha over beta factor of least remaining size. And so the fact that scale is only making errors by a factor of alpha over beta means that its R work can be compared to SRPT's alpha over beta R work. So we use that same slack factor of alpha over beta. And so that's kind of the vague intuition for why this lemma is true. And so once you have this lemma and you have WINE and you have Little's Law, you put them together and you get this theorem that says, and this is a pretty simple computation once you have the lemma. And this says that mean response time of scale is at most alpha over beta times mean response time of SRPT. So that's how we use WINE to compare scale to SRPT. So a few more comments about things on this slide. First, I want to mention that WINE also holds in the worst case. In fact, it holds very generally. The theorem is really that if you look at any system, it doesn't matter kind of how the system got to its current state, if you just take a picture of its current state and you count the number of jobs and then you do the R work integral, you get the same thing. So that's the first thing I want to say. The second thing I want to mention is that this lemma and theorem can be generalized slightly. So remember that I mentioned earlier that scale isn't a policy you could actually do, because you have to know a job's true size in order to scale linearly down to it. But if you were in a system where you had not just an initial size estimate, but a dynamically updating remaining size estimate, then you probably couldn't do exactly scale, but you might have a sort of noisy version of scale that you could do. And this lemma will also work if you're doing some sort of noisy version of scale. So that's what I wanted to say about Wine. In summary, what Wine does is it reduces the mean response time comparison to an R-work comparison. And we showed that the R-work amounts were close enough between scale and SRPT that they have similar enough mean response times. Okay, let's summarize what we talked about today. So we discussed the problem of minimizing mean response time when we only have access to noisy size estimates. And this is a difficult problem because the natural policies we'd think of end up performing badly. For example, the naive translation of SRPT into size estimate world ends up not even being consistent. So it has poor performance even when the noise is very low. So to solve this problem, we came up with a new policy which has provably good performance. Specifically, we showed it is 1 consistent, so perfect consistency, and 3.5 graceful. And we proved this result using a creative cocktail of 2 recently developed tools from queuing theory. And so I'm excited about this general direction of algorithms with predictions, where we kind of consider stochastic versions of the problems. And I'm interested in developing tools, theoretical tools for analyzing these stochastic problems that go beyond just scheduling and queuing. So if you're curious to talk about algorithms with predictions, or you have any questions about this talk, feel free to get in touch. I'd be delighted to hear from you.